What is the main problem that the proposed WeMath benchmark aims to address in evaluating visual mathematical reasoning in LMMs?
The main problem that the proposed WeMath benchmark aims to address in evaluating visual mathematical reasoning in LMMs is the insufficient knowledge (IK) issue. The benchmark focuses on assessing LMMs' mastery of fundamental knowledge concepts, which is crucial for their reasoning abilities. By decomposing complex mathematical problems into more manageable subproblems based on knowledge concepts, WeMath aims to identify and tackle the lack of foundational knowledge in LMM's reasoning processes. The benchmark introduces a hierarchical metric that categorizes reasoning capabilities into insufficient knowledge (IK), inadequate generalization (IG), complete mastery (CM), and rote memorization (ERM). Through this detailed evaluation process, WeMath aims to highlight and address the IK issue, which is identified as the greatest vulnerability of LMMs in visual mathematical reasoning.
How does the proposed method for evaluating visual mathematical reasoning in LMMs work step by step?
The proposed method for evaluating visual mathematical reasoning in LMMs works step by step as follows. 1. Problem decomposition. Real-world mathematical problems are decomposed into individual subproblems based on the invoked knowledge concepts. Human experts break down complex problems into more manageable subproblems by identifying the fundamental knowledge concepts involved in each step. 2. Data representation. Each test sample is represented as Q_I, I_I, A_I, vert K_I, C_I, where Q_I is the text question, I_I is the image, A_I is the answer, K_I represents the knowledge concepts within the question, and C_I denotes the prerequisite conditions needed to solve the problem. 3. Knowledge-based data decomposition. The multi-step problem is recursively decomposed into M1-step subproblems based on knowledge concepts. Each subproblem is formulated as K_I, C_I, where K_I is the individual knowledge concept and C_I is the prior condition for the subproblem. 4. Reasoning evaluation. The responses from both the M1-step subproblems and the original problem are classified into 4 categories: insufficient knowledge (IK), inadequate generalization (IG), complete mastery (CM), and rote memorization (ERM). These categories assess the model's proficiency in solving individual knowledge concepts and composite problems. 5. Metric establishment. A reasoning capability hierarchy is established as IK less than IG less than CM, where models are evaluated based on their ability to progress from insufficient knowledge to complete mastery. The unreasonable scenario of rote memorization is also identified and addressed through a flexible, loose metric. 6. Quantitative analysis. The effectiveness of the proposed knowledge concept augmentation (KCA) strategy is quantitatively analyzed to evaluate the performance improvements in LMMs. The KCA strategy aims to alleviate insufficient knowledge issues and enhance the reasoning capabilities of the models. 7. Error analysis. The occurrence of different types of errors across the 67 knowledge concepts is analyzed to identify common pitfalls in visual mathematical reasoning. Knowledge errors and visual errors are assessed to pinpoint areas for improvement in LMM's reasoning processes. By following these steps, the proposed method provides a comprehensive framework for evaluating the visual mathematical reasoning abilities of LMMs, focusing on knowledge concepts, problem decomposition, and reasoning proficiency.
What are the theoretical or practical benefits of using the hierarchical knowledge structure in WeMath for evaluating LMMs?
The theoretical and practical benefits of using the hierarchical knowledge structure in WeMath for evaluating LMMs are significant. The hierarchical knowledge structure ensures a rigorous and multi-category architecture based on knowledge concepts from mathematics textbooks, providing a systematic and comprehensive framework for evaluating LMM's reasoning abilities. This structure allows for the independent assessment of knowledge concepts at different levels, enabling a detailed analysis of LMM's grasp on fundamental mathematical principles. By breaking down complex mathematical problems into more manageable subproblems based on knowledge concepts, the hierarchical structure facilitates a granular evaluation of LMM's reasoning processes, leading to a more accurate assessment of their capabilities. In practical terms, the hierarchical knowledge structure in WeMath helps in identifying specific areas where LMMs may struggle, such as insufficient knowledge, IK, inadequate generalization, IG, complete mastery, CM, and rote memorization, ERM. This breakdown allows researchers to pinpoint the exact stage at which LMMs face challenges in solving mathematical problems, guiding the development of targeted strategies for improvement. Additionally, the knowledge concept augmentation strategy in WeMath provides essential knowledge support for LMM's reasoning processes, helping to address the foundational challenge of insufficient knowledge, IK, commonly observed in LMMs. Overall, the hierarchical knowledge structure in WeMath enhances the precision and depth of evaluation for LMM's visual mathematical reasoning capabilities. It offers a structured approach to assess LMM's mastery of knowledge concepts, enabling researchers to gain insights into the model's reasoning abilities at different levels of complexity. This structured evaluation framework not only aids in identifying weaknesses in LMMs, but also guides the development of strategies to enhance their reasoning and problem-solving skills, ultimately advancing the field of visual mathematical reasoning in large multimodal models.
How are the inherent issues in LMM's problem-solving abilities evaluated using the four-dimensional metric in WeMath?
The inherent issues in LMM's problem-solving abilities are evaluated using the four-dimensional metric in WeMath by categorizing the responses into four distinct conditions: insufficient knowledge, IK, inadequate generalization, IG, complete mastery, CM, and rote memorization, ERM. IK occurs when one-step problems contain errors and the multi-step problem is wrong, indicating a lack of understanding of single knowledge concepts. IG is identified when one-step problems are correct, but the multi-step problem is incorrect, showcasing a struggle in generalizing knowledge to solve composite problems. CM is achieved when both one-step problems and the multi-step problem are answered correctly, demonstrating reliable and accurate results. ERM is flagged when one-step problems contain errors, but the multi-step problem is answered correctly, contradicting human logical thinking. The four-dimensional metric helps to assess the model's proficiency in reasoning by highlighting the model's struggles with single and multiple knowledge concepts, its ability to generalize knowledge, and its overall mastery of problem-solving abilities.
What are the key observations regarding the performance of different LMMs on one-step, two-step, three-step problems, and different problem domains based on the results presented in the paper?
The key observations regarding the performance of different LMMs on one-step, two-step, three-step problems, and different problem domains based on the results presented in the paper are as follows. 1. GPT-4o consistently outperforms other LMMs across all settings, demonstrating an advantage in solving problems of varying complexities, one-step, two-step, three-step. 2. Closed-source models like GPT-4v and Gemini 1. 5 Pro also exhibit competitive performance in visual mathematical reasoning tasks. 3. Most LMMs struggle significantly more on multi-step problems compared to one-step problems, with GPT-4o's accuracy dropping notably from 72.84% to 43.64% on multi-step problems. 4. Larger parameter scales in LLMs generally lead to better generalization abilities in visual mathematical reasoning tasks, indicating the importance of the text decoder's parameter scales. 5. LMMs excel in calculations but face challenges with fine-grained visual measurements, particularly in areas like angle measurement and unit conversion. Quote 6. LMMs show potential for parameter compression with models like Phi-3 Vision 4. 2B and Mini CPM Llama 3v2. 5 demonstrating competitive performance despite having smaller parameter scales. 7. GPT-4o stands out in addressing the insufficient knowledge (IK) issue, with its main challenge shifting towards inadequate generalization (IG), positioning it as the first LMM advancing towards the knowledge generalization stage. 8. The unreasonable rote memorization (ERM) issue remains prevalent across most LMMs, with GPT-4o leading in addressing this issue, particularly on the loose metric. 9. LLAVA Next 110B shows performance closest to GPT-4, indicating strong potential for parameter compression and optimization of visual representations. 10. The paper emphasizes the significance of addressing insufficient knowledge, IK, as the foundation challenge in mathematical reasoning, and highlights the effectiveness of the proposed knowledge concept augmentation (KCA) strategy in alleviating IK issues in LMMs.
Based on the paper, what are the limitations of the proposed KCA strategy for addressing the insufficient knowledge (IK) issue in LMM's reasoning process?
The limitations of the proposed KCA strategy for addressing the insufficient knowledge (IK) issue in LMM's reasoning process are that while the KCA strategy significantly alleviates IK issues, it does not noticeably improve inadequate generalization (IG). The KCA strategy primarily focuses on addressing gaps in reasoning knowledge through knowledge descriptions derived from Euclid's Elements and textbooks. However, enhancing IG issues requires a more comprehensive enhancement of the LMM's knowledge generalization abilities. This limitation is highlighted in the quantitative analysis of LMMs with KCA, where consistent performance improvements are observed on both strict and loose metrics, but the strategy does not lead to significant improvements in IG. The text emphasizes that the KCA strategy primarily targets filling the gaps in reasoning knowledge, which aligns with human intuition, but acknowledges that enhancing IG issues requires a broader enhancement of LMM's knowledge generalization abilities, indicating a direction for future exploration.